From a single eigenvalue equation, we can determine whether a system oscillates, decays instantly, or slowly returns to equilibrium. This lecture derives the full solution and explains the exact physical meaning of every damping term. Well then, first, we again set the external forces equal to 0, so that we obtain the homogeneous equation. We must now bring the prefactor of the inertia term to 1, which is why we divide the entire equation by m. This makes the prefactor of y double dot equal to 1, and the m shifts into the denominators of the other prefactors. If we now recall the solution approach for a homogeneous equation of second order, and once again insert this ansatz together with its derivatives into our homogeneous equation, we obtain the following relation. As before, we cancel the factor e to the power of lambda t, and in this step we also substitute the prefactors of the damping and stiffness terms. By substituting d over m with 2 delta and k over m with omega 0 squared, the characteristic eigenvalue equation results as lambda squared plus 2 times delta times lambda plus omega 0 squared is equal to 0. This is the starting point for our eigenvalue solution. Now let us recall from school times how we solved polynomials of second order, namely how we determined the roots of quadratic polynomials. The equation was a times x squared plus b times x plus c, where the c can also be written as c times x to the power of 0. To solve this quadratic polynomial, we used back in school and also later the quadratic formula. This quadratic formula, which can also be applied here, only that instead of x we have lambda as the unknown. Now we apply the quadratic formula to this equation and obtain, after simplifying and rearranging, the eigenvalues as lambda 1, 2 is equal to minus delta plus minus square root of delta squared minus omega 0 squared. With this, we can determine the eigenvalues depending on the system parameters k, d, and m. Depending on the term under the square root, 3 different solutions for the eigenvalue lambda arise. We see that the part under the roots, also called the discriminants, can be positive, negative, or 0, depending on the ratio of delta to omega 0. In the first case, delta is smaller than omega 0. Then it quickly becomes clear that the discriminant is negative, which means we have a negative part under the root. This leads to a complex solution where we must pull out minus 1 from the root using the imaginary units j. Thus, in case 1, the eigenvalue lambda 1, 2 is equal to minus delta plus minus j, square root of omega 0 squared minus delta squared. In the second case, delta is equal to omega 0. Then, the part under the square roots becomes 0, and we obtain a purely real solution with a double root. That is, lambda 1 is equal to lambda 2 is equal to minus delta. In the third case, we again have real eigenvalues, but now 2 different ones. Lambda 1, 2 is equal to minus delta plus minus square roots of delta squared minus omega 0 squared. This happens only when delta is larger than omega 0. These are 3 different cases that can occur depending on the system parameters. We can either have a complex eigenvalue solution, meaning an oscillation occurs, or we can have no oscillation, namely when the eigenvalue is purely real, as in case 2 and case 3. Let us illustrate what these 3 different cases of the eigenvalue mean. It is important to visualize this carefully and to understand what the mathematical background causes in a physical world. We now again consider the 1 degree of freedom oscillator on the left. which we have displaced upward by an initial value y0. Now let us sketch what happens, how the solution y of t behaves over time in the three different cases. In case 1, with a complex eigenvalue, we have an oscillation. The displaced one-mass oscillator decays over time. The amplitude y0 decreases with time. This is determined by the decay constant delta. And one can see clearly the envelope, shown in green, which scales down the initial amplitude with the factor e to the power of minus delta t over time. This means for increasing time values, this factor becomes smaller and the amplitudes decrease. If the decay constant delta was 0, the oscillation would continue undamped infinitely with the same amplitudes. This is shown here with a dashed line. If we set delta to 0, then e to the power of 0 becomes 1. This means the oscillation would go on forever. This case, a set, occurs when delta is smaller than omega 0. This relationship is best described by the so-called slurless damping ratio, also called the modal damping, defined as capital D is equal to delta over omega 0. As long as the decay constant delta is smaller than the undamped natural frequency omega 0, we are in case 1, in which capital D is smaller than 1. This means oscillation is possible. In case 2, we have the double real eigenvalue, where delta is equal to omega 0. Here, the modal damping D is equal to 1. This is the critically damped case, where the system just does not oscillate. The initial displacement returns to the equilibrium position as quickly as possible, but without overshooting. This case leads to the fastest return to the unloaded equilibrium state. In case 3, we again have real eigenvalues, but not the double roots, rather two different ones. This case occurs only when we have a modal damping greater than 1. Greater than 1 means delta is greater than omega 0. This state is overdamped, and the system is not capable of oscillating. The system creeps slowly from its displaced state back to its initial state. With very strong damping, this can take a very long time, since the damper exerts high forces even at small velocities. If you want to learn more about the characteristics of dynamic systems in mechanical engineering, check out the first link in the description. To understand the function of the eigenvalue better, let us next turn to the visualization and interpretation of the eigenvalue. Mathematically, the eigenvalue itself is a complex number. This can be divided into a real and an imaginary part and represented in the complex plane. The imaginary part is the part multiplied by the imaginary unit j. This is plotted on the vertical axis on the imaginary plane. The real part, on the other hand, is equal to minus delta and is plotted on the horizontal axis of the complex plane. The magnitude of the vector lambda is obtained from trigonometry. It is described as the square roots of the imaginary part squared plus the real part squared. The magnitude of this eigenvalue thus corresponds to the undamped natural frequency omega 0. For a complete solution, however, we are also interested in the damped angular frequency omega d. This results from omega 0 and the decay constant. Omega d is equal to the square root of omega 0 squared minus delta squared, or in other words, omega 0 times the square root of 1 minus d squared. This makes sense. In the undamped case, the modal damping is 0, and then omega d turns to omega 0. In the critically damped or overdamped case, where the modal damping is equal or greater than 1, no oscillation occurs, and therefore omega d is equal to 0. In the plotted diagram, we see schematically a lightly damped oscillation, as well as its envelope, given by the term e to the power of minus delta t. Another important parameter for analyzing damped systems is the logarithmic decrement. By counting peaks and the corresponding elapsed time, you can determine system parameters such as the period of the damped oscillation Td or the decay constant delta. For this purpose, you record 2 successive peaks and determine the logarithmic decrement. The same can also be done by measuring over several periods to reduce the error due to reading inaccuracy. In this case, you count n peaks further and divide the logarithm by n. Here, Td is the period of the damped oscillation, the reciprocal of the damped angular frequency. Both Td and the peaks of an oscillation can be measured experimentally, which allows determining the decay constant in this way.